Hi all, my name is Dakota Parker, and this is my final project presentation for CS223. My project was the generalization of DQL strategies in multiplayer Chinese checkers. My goal with this project was to generate a DQL model that I could train in a two-player environment and then see how it generalized to three, four, and six-player environments. I was able to generate a DQL model that in a two-player environment had an 83% win rate against the heuristic baseline model. When then taking this model and running it in three, four, and six-player environments against the same heuristic model, it had a 63, 62, and 30% win rate respectively. This showed that the model that was trained in the two-player environment was able to effectively learn strategies that it could generalize to the higher environments. It had the highest win rate across all of these environments. The data that I used to train this model was a bootstrap data set generated by play with the heuristic model. This is how I originally populated the replay buffer, and I would run one training iteration on this, and then I would have the trained model play the heuristic model, and then add those experiences to the replay buffer so it could learn what works and what doesn't. Now, the features I used to represent the game here, I kept very generic because I didn't want to be designing features that I thought would win. I wanted the model to learn those on its own. So for the encoded game state representation, I gave three grids of zeros and ones. The first grid was the player positions, the second grid was the target positions, and the last grid was the other player positions. Now, the other player positions was important because I didn't give a distinction. The model does not know the difference between player two and player three in higher environments. This made it very easy to take the model that I trained in the two-player environment and run it in the higher environments effectively. I used similar grid encodings for the move. The reward encoding, the reward function that I used, I originally tried a sparse reward to give a one for a winning game and a negative one for a losing game. However, the model was not able to learn this very effectively. So I had to introduce intermediate rewards based on distance of the move and direction of the move. The model architecture that I used for this was I had two convolutional neural networks, one that processed the game state and one that processed the move state. I then I then concatenated the outputs of these and I passed those into the DQL network. The DQL network was then intended to learn the discounted returns from the end game state. So given it would end in a one, a winning game, the experiences throughout that game would be discounted from that end one. And so this allows the model to, instead of learning intermediate rewards like longest move, it can find different strategies that end up in a very high long-term reward. Now, the training environment I used for this, I used a replay buffer, which is standard for reinforcement learning, but I modified it so that it didn't have as many duplicate experiences that come from common gameplay in the early game. So I limited it to 50 moves, 50 samples of a unique move. And so given many game states can have the same move, there's only allowed to be 50 of them in the buffer. I also had to add a bias in sampling towards winning games. This model wasn't able to win early on, and so to show it winning experiences, I had to bias it in training to see these winning games. The biggest thing in the training environment, though, that led this to stable convergence that I was able to reproduce for a few different versions of this model was the genetic algorithm. Now, to do this, I would train in each iteration 50 different models based off of the previous. I would take each of these 50 and I would run them against the baseline in 50 different games, and then I would see their win rate in those games. And now, if their win rate beat the win rate for the parent, then that model was taken and it was used as the next one. You can see in this graph on the right, these lines represent where a new generation was. And so you can see our stopping criteria for training here was when the parent could not be beat by any of its descendants. Now, the result of this was we had that 83% win rate in the two-player environment, and this was reproducible using our training workflow multiple times with different lengths of time to get to this winning state. Something interesting was that we saw the regular error decrease, but the discounted error did not decrease that much. This tells us that this model was learning those intermediate rewards a lot better than it was learning those long-term discounted rewards. This is because a lot of the gameplay had a lot of random actions that aren't that informative of a long-term discounted reward. It can be confusing to learn. I think that if we gave this thing a more diverse data set with more thoughtful strategies, it would be able to more effectively learn this discounted error. Now, I want to show some of the gameplay here to give an idea for what happened. This model was able to really effectively learn early game strategies, which is why it was able to generalize into the higher environments and have such a high win rate. So you can see it gets this really effective strategy of jumping early on that it is able to then apply in these higher environments. So showing the three-player game here, you can see that it similarly takes the same first move, and although it doesn't do as many jumps, it is still able to come to a winning game state. And then to show for four players, just to get through all of these, you can see here that this has a bit more interference than with its neighbor. Takes that same first move, um, and then it takes advantage of a lot of large jump moves, which it recognizes have a high reward. And then finally, in the six-player game where there's a lot more interference, you can see this model was able to take advantage of a few long jump moves and eventually get to the winning game state first. Now, if I had more time with this model, I would have loved to taken this into self-play with the DQL model playing another DQL model, and then eventually evolve this into co-evolution using a tournament style to play these things against each other and cut out generations that don't do well and have ineffective strategies while rewarding the ones and making many off spring like spawns of the winning strategies and see how those evolve over time. But yeah, didn't have time for that. So overall, I think this was a very successful project. I'm happy with the results and I learned a lot through it. So thank you for your time and I appreciate you for listening.